Welcome to lesson 4.7 on graphing linear equations. So in this lesson, we are going to talk about how we will use function notation. We've already talked about in past lessons how to actually graph the equations and functions, so this will be slightly different. All right, so one thing we need to know about function notation right away. You've seen function notation before in the form of y equals mx plus b. Um, Function notation basically adds this f of x idea right here. Okay, f of x is just another name for y, and it is read as the value of f at x or f of x. Okay, it does not mean f times x. Okay, you can use the letter f, g, or h to name the functions. So let's look at some examples with this. So I have, what is the value of the function f of x equals 3x minus 15 when x equals negative 3? And we have options of either A, negative 24, B, negative 6, C, negative 2, or D, 8. So what we're going to do is we're actually just going to, it's very simple, we're just going to take that x equals negative 3 and we are going to plug it into our function. So we are going to right away f of, this is where the f of x comes in, f of negative 3. This just means that we're finding the function at x when x equals negative 3. And then we're going to substitute negative 3 into x. We're going to go 3 times negative 3 minus 15. I don't need to do anything on this side of this equation. This is just to tell the person who's looking at your work what exactly you're doing. We just need to focus on solving this part. So that's what I'm going to do in this next step. So I'm just going to do 3 times negative 3, which is negative 9. Negative 9 minus 15, which is negative 24. All right, so then the correct answer would be A. All right. Another example that we could look at is if we are evaluating the function h of x, equals negative 7x when x equals 7. So I'm going to plug it in just like I did before. So I'm going to go h times 7, or h of 7, excuse me, equals negative 7, plug in 7 for my x, times 7. Again, like I said before, I do not need to do anything with this side. I'm just going to solve. So negative 7 times 7 equals negative 49. So my function of h of x when x equals 7 is negative 49. Okay? All right. The next bit of information, or the next example, I'm sorry, that we're going to do is just looking at the, if they give you that f of x equals negative 6, or some sort of number in this case, how would we solve for this function? Okay, so we want to find the value of x when f of x equals 6. So instead of substituting x for a number, I'm actually going to substitute f of x for a number. So I'm going to turn f of x into 6, and then I'm just going to solve like I normally would for x. So I'm going to add 10 to both sides, so then I'm going to get 2x equals 16 divided by 2, and that will get me 8. All right, so when x equals 8, f of x equals 6. This is our answer. All right, one more example before we move on to the next part. This is a very common word problem of a real life situation when we would need to graph the function. So in this case it says the gray wolf population in central Idaho was monitored over several years for a project aimed at boosting the number of wolves. The number of wolves can be modeled by the function f of x equals 37x plus 7, where x is the number of years since 1995. And we want to graph the function and identify its domain and range. If you remember from the past, domain means x, range means y. So I'm just going to go through and look at my solution. So to graph the function, I'm going to make a table. So I'm going to pick my x values. In this case, I just picked 0, 1, and 2. Since we're dealing with years, it is not necessary to choose negative numbers just because we're not talking about years prior to 1995. We're just talking about years beyond 1995. So we're going to then plug that into the original equation, into my function of x. And I'm going to do 37 times 0 plus 7 equals 7. Plug 1 in for x here. 37 times 1, 37 plus 7, which should equal 44. Same thing for 2, 37 times 2 plus 7, which would be 81. So this, in this case, is my domain. And these numbers right here are my range. Okay. All right, so then if I were to graph it, I would just graph it on a normal XY coordinate plane. And I'm usually going to make my years, or in this case my functions, since they're so small, just one across, but then my y-axis is going to go by 20s just to make it easier to graph, so I'm not having to make giant graphs. Okay, so then I'm just going to plot the points. My first point is 0, 7. Next point is 1, 44. My next point is 2, 81. So the domain, like I said, is anything above 0, okay? Because if you look, it's just going to keep going. X is just going to keep going on and on and on forever. And my range is anything, because my lowest number is, my y-intercept is 7. It's going to be anything larger than 7. All right, so if I wanted to use the model from that last example we just looked at to find x, so that f of x equals 155, and then I want to explain what the solution means in this situation. So I'm going to look at my function again, just go back. It's 37x plus 7. So I'm going to go f of x equals 37x plus 7. Double check I got that right. Yep, okay. And then I'm just going to plug 155 in for my f of x. So I'm going to get 155 equals 37x plus 7. And then I'm going to solve like a normal equation. I'm going to subtract 7 over here. 155 minus 7 is 148. And then I've got that equals 37x. And if you've already guessed it, we're going to divide by 37. And then 148 divided by 37 is equal to 4. So in the context of this question, that 4 means that if you look at the original problem, x is the number of years since 1995. The 4 means that after 4 years, the wolf population will be 155. All right, so a couple more things with this graphing linear functions idea is that idea of domain and range. Just to review, the domain of a function consists of the values of x, for which the function is defined, meaning our x values, and then the range consists of the values of f of x, or y as we've been calling it, same thing, where x is the domain of f, okay? So if we were to graph the functions, it would be x, f of x, or we've talked a lot about just x, y. These are interchangeable, okay? So the next idea is that every function has like a family of functions, or in this case, a parent linear or a parent function. Okay, today we're just going to be talking about the linear functions. So a family of functions is just a group of functions with similar characteristics. For example, we're dealing with lines. At some point we might be dealing with parabolas or absolute value. Okay, so today we're just going to focus on the lines. And in this case, we know that the functions we've been dealing with are f of x equals mx plus b, or y equals mx plus b. Okay, so our parent function for our linear function is just f of x equals x, meaning y equals x. If you notice that my intercept would just be 0 because there's nothing after that, so we're starting at the origin. And then my slope would be, because every variable has a 1 in front of it, it would be 1 over 1, which is why we are just rising and running by 1. So that's what our parent linear function looks like. We can use this parent linear function to actually compare with graphs. So in this case, we have g of x equals x plus 3. So we know that our intercept in this case is going to be 3, and our slope is, because there's an invisible 1 in front of that x, it's going to be 1 or 1 over 1. Okay, so my slope is going to be the same. However, if you look here, this blue line is my parent function. Because I had an intercept, I started at 3, so right here, and then I rose and ran by 1. So we could say that these two functions, because the graphs of g and f have the same slope, the lines are parallel. Okay, parallel lines always have the same slope, but that the y-intercepts are different. Okay, it's 3 more. All right, so then let's look at another example. We have h of x equals 2x. So in this case, I know that my intercept is 0 because I don't have a plus anything, so I know it's going to be 0. And my slope is going to be 2, or I'm just going to write it as 2 over 1 so I can see my rise and run. So then if I were to graph my line, again, the blue line is the parent function. The red line, remember I started at 0 because that's my intercept. I rise 1, 2, run 1, rise 1, 2, run 1. If I want to go the other way, right there, okay? So then I get my line. So we can say that they have the same intercept as the parent function, but different slopes, okay? Because the slope of the graph h is greater than the slope of the graph of f, meaning 2 is bigger than 1. The graph h rises faster, okay? So do you see it's steeper? And the y-intercept is just 0, like I said before, okay? All right, so just to wrap up all of the ideas we talked about in this video, when we're comparing graphs of linear functions to its parent function, f of x equals x or y equals x, okay, we're always comparing them in this mx plus b form, our slope-intercept form, and that we can have parallel lines where the slopes are the same but the intercepts are different. I can have situations like this where they call them vertical stretches or shrinks because they have the same intercept, however, they're either steeper or not as steep as the parent function. And then we can even have situations where um, they have the same intercept, but they have negative slopes. So you see how these two red lines have negative slopes. Okay, so that's all I have for you for graphing linear equations. Please let me know if you have any questions. Thanks.